All right, so I'm talking about slope today. There, what I'm going to be focusing on this session is just the concept of slope and how it applies to real life and just kind of what it means. There's another one that focuses more on using the formula with ordered pairs and lines. That's less, conceptual what it means and more about just like being able to use, do the math part. So yeah, so this is focusing just on the concept because the concept is so important. And you talk about slope a lot in life, you don't even realize that's what you're discussing. So that's sort of what I'm focusing on here. So to understand slope, you first need to understand what we're talking about, which is linear equations of two variables. There's an x and a y, and when you graph these, you get a line. So that's the word linear literally has the word line in it. So whenever we're talking about lines that we're graphing, those are linear equations. And so these are the various forms of the equation of the line that you can see that, and that's how you tell that it's going to be a line if it's in one of these forms. If you've got no variables or no exponents on your variables, on your x and y, and you can have the x and y on the same side, they can be on opposite sides. There's different forms of the equation. And in the standard form, you don't see slope, but this value of m that is in slope intercept form and point slope form, that is slope. And that's what we're going to be talking about. And it's so we use the letter m for it. So slope is a number that tells us how slanted a line is, and then it gives us a sense of direction. It's different from the angle of a line because the angle is measuring, let me draw a picture here. So I'm going to just draw, supposed to be straight. So that's our line. And let's say we've got our horizon here. So the angle between our line and the horizon, that's angle, but that is not slope. So slope is looking at how much you're changing vertically over how much you're changing horizontally. So it's instead of looking at like the angle between the two lines, you're looking at distances. And so you're looking at, okay, well, how high am I going over some distance here? And the ratio of that is slope. So we're measuring the steepness, and it's just a different way of measuring steepness from angle. Because like if you think about angles, you know that like 90 degrees is straight up. So that's definitely steeper than like 45 degrees. The ratio here that we're using for slope is just an alternate way to measure steepness. And essentially a zero slope means that it's flat. And then as it's going up, we're getting to positive numbers for slope. And like equivalent to a 90-degree angle would be like infinite slope. And then if you go in the other direction, we have negative slopes, which means that it's going down from the horizontal. So while angles we usually talk about between 0 to 360, slope can basically go from like negative infinity to positive infinity. So it's different way to reference, what you're looking at here. So they're both indicating how steep something is. It's just they've got different reference points and we're looking at different values here. So you do want to make sure that you don't get confused between those. So when we're talking about slope, if you ignore the sign, whether it's positive or negative, and you just look at the actual number, the bigger the number, the steeper the slope. So a slope of 2 is bigger than a slope of 1, or steeper than a slope of 1. A slope of -2 is steeper than a slope of 1 because you just ignore the sign. The sign is giving us essentially just the direction, whether we're going up as we move from left to right, or whether we're going down as left to right. So that's what the sign of the slope means. And the fact that we, have a way to compare is what really makes slope powerful, because if you have a slope of 2 and a slope of -2, that those are the same steepness, just in different directions. One's going up, one is going down. When you've got angles, it's a little harder to make that same comparison, because like if you had an angle 45 degrees, kind of its mirror image would be, oh gosh, 270 plus 45. I don't even know what that, I'd have to subtract 45 degrees from 360. So I'm not going to do that in my head, but you have like a different angle, and it's harder conceptually to understand that those are the same steepness, because you'd be comparing 45 degrees to like it's probably like 315 or something like that. You don't really, with those angles, it's not obvious that those are actually going to be the same steepness of the line. So slope is very powerful because it gives you an easier way that makes more sense conceptually to when you're comparing lines. And the steepness, plus it's easier to determine, is it going up or going down. With angles, you have to know, okay, 180 is horizontal, so then you have to kind of know your angles, and it's just not as intuitive. So slope is also called the average rate of change. And this is where you've done slope in your life and you've not realized you've been talking about slope, because we often in real life talk about rate of change, how much something is changing, and we look at averages of that. So real life slopes are anything that is a rate, where there's like one unit divided by another unit per something else. So speeds are technically slopes because we're measuring how much we're changing. So miles per hour, kilometers per hour, feet per second, any kind of speed is a measurement of slope. Cost per time, your salary, that is part of slope. How much you're getting paid per month or per hour. If you're looking at ratios, and you're comparing, like in recipes, how many cups you need for a certain serving, or if you're comparing prices in the store, prices per ounce, to see kind of which one is cheaper per ounce, you're actually talking about the concept of slope. And this is really important because any of these concepts, speed, salary, those, if they have a slope, if they meet this definition of slope, that means that the equation to represent this is a linear equation. So it tells you, if you understand, like, okay, this is some amount of change, that tells you that the equation you write, that if you wanted to like predict or represent, model these, it's going to be a linear equation. Other types of slope that, is pitch of a roof, the grade of a road, which is interesting because that's usually the grade of a road is given as percentages. If you've ever been, if you're in a mountainous area, they might give like it's a 5% grade or 15% grade, and it's a percent, but it's still measuring the amount of change. They've just put it into percent form. And so that is actually measuring the slope of the road. Variable costs of things. So this happens a lot in business. So this is a concept that's so important in business when you're talking about how much does it cost per unit to produce something versus how much am I getting, back in revenue per unit. Those, you might have different pieces that all cost different amounts, but those are all basically how much something changes, and that is slope. So slope is everywhere in the world. You may just not know that that is what you're talking about. We usually don't use the word slope unless we are putting it in context of an equation or a graph. So if we're not writing an equation for it or we're not graphing it, you'll usually see things like average rate of change. It's when we start putting it into more algebraic terms that we use the term slope. So I've mentioned this a little bit. Things you can do with slope is you can compare the steepness of two lines to see, what is steeper. You can determine the direction, whether it's going up or it's going down. You can determine if lines are parallel to each other or perpendicular to each other. You can compare rates graphically and numerically. So graphically is, you're looking at the change in steepness. If you've got things that are graphed, you're looking at, well, which one's changing faster? So that's really, you're comparing the slopes when you're looking at that. And numerically is the same thing. Usually that's when you're like in the store and you're comparing your price per ounce of like two different brands of the same thing. That's usually where you're comparing them numerically. And you're looking at, okay, which one is cheaper? You usually want the smaller one. Average rates of change. So this is something like, let's say you're looking at the price of stocks over time. It's going to go up, go down. There's a lot of variability, but you can kind of put a line that's kind of like the average over time, where you're saying, okay, over this long period of time, is it basically going up, going down? And so that's what the average rate of change is just to kind of ignore all the little things going in and take like 2 points far apart and say, okay, on average, has it been going up or going down? So that's average rate of change. That is the slope. So that's good with stocks, because you'd want to know if on average it's increasing, because if not, then you might want to sell that one. Or maybe you want to buy because it's going down, it's cheaper. And if you know the slope and you have 1 point, you can graph a line with that. That's all you need to graph a line, is one starting point and the slope, and then you can graph the line from there. So there are a lot of things that you can do with slope. It's very useful in the real world once you kind of like understand what it is. And of course, it's useful in algebra and calculus, which is like 2 courses from this one, 3 courses from this one. You've got college algebra, pre-calculus, then calculus. Calculus is basically the study of slope, but extending it beyond lines. So you're looking at how things change, but they're not lines anymore. They're like curves. And so that's what calculus is, because in real life, there are a lot more things that are not lines, that are curved. And so calculus is just taking this concept and expanding it out. So our equation of slope, so there's lots of different forms for this. And the version I'm focusing on is this part right here. We're not going to kind of do the y2 minus y1. So we're actually going to just look at this. So we use the letter M for slope. And it is a ratio of basically your rise, which means how much you went vertically. So that's your change in y, divided by how much you're changing horizontally, your change in x. So we call that rise over run. So it's just a ratio of those. And the triangle symbol, oh, I didn't mean to erase that. The triangle symbol here is just a Greek letter delta that represents change. So that's just a symbol that we use for change. So when we're looking at the change, you're basically, if you were on a graph, you're subtracting your top value minus your bottom value, or horizontally, your second minus the first to get how much it changes in between. So that's the y2 minus y1 over x2 minus x2. But you're basically, okay, what is the difference or the distance between these 2 points horizontally and then these 2 points vertically? And that you divide those, and that gets you your slope. And so y is always going to be on top of your slope. A lot of people will get confused which one's on top, which one's on bottom. It's always rise over run. The y is on top. So if you get it reversed, your slope is going to be it's like the opposite, the reciprocal. So for vertical lines, I mentioned it's like an infinite slope. That's where you get undefined, because according to the equation, you're dividing by the change in X, but if it's vertical, you're not moving on your X at all. There's no change in X, which is 0, so you're dividing by 0. So that's an undefined slope. And then horizontal lines, you have no change in Y, so you got 0 on the top of the fraction, and 0 divided by anything is 0. So those are two special slopes. And then, as I mentioned before, you either have positive, which is going up as you move left to right, and negative as you move down from left to right. And we're always looking left to right, like the order that we read. So this is, again, just putting this into concept of what it looks like, when I'm doing my hands, what a 0 slope looks like, what undefined looks like, positive and negative. And then there are some, how we compare slopes with parallel and perpendicular lines. So parallel lines have the same slope because they're going in the same direction, the same steepness and everything. Perpendicular lines are going in opposite directions. So one is increasing, the other one's decreasing. And essentially, if you multiply those slopes together, you get -1. And then you can solve that equation, and that gives you how to get the slope of the other one. So this is just, if you're comparing two lines, which is something that happens a lot in business, actually, knowing whether they're parallel, perpendicular, and what that means is really important visually to kind of understand what it means. But the parallel perpendicular lines, that's another thing separate from what I'm covering today, but just so you kind of get some concepts here. So are there any questions on what I've been talking about conceptually before I start getting into examples? Okay. And get this. All right, so we're going to start with the real world. So I've got a roof here. So we want to find the slope. So this is the pitch of the roof. And so you're looking at how much does it increase. And actually, so you on the roof, you've got one side going up, one side going down. We usually, when you're given like the pitch of a roof, you don't usually use the downside version or the negative value of slope. You usually talk about the positive, but these will be the same numbers. They're just going in opposite directions. But the slope is how much you are rising over your vertical distance. So, it's not in the, it was still in the highlighter. So your slope M, think of it as a rise over the run. So with the roof, our rise is how high the roof is going. We're going to start at like the bottom of the roof. You're going to consider it 0, and then it goes up 8 feet from that point. So the rise is 8 feet. And then horizontally up till we get to the tip, that's a distance of 24 feet. So the run is 24 feet. And so our slope, the units here are really important when you talk about slope, because slope usually has either no units because they cancel out, or there are units in slope. So that's why I made sure to write my units here. So in here, the units will cancel out. So you can cancel units out just like you can cancel out numbers. So since there's feet on top, feet on the bottom, the units essentially cancel. And then we've got 8 over 24, which then you can reduce. So I can divide both of those numbers by 8. So I'm going to write that down. So you always want to reduce your slope. You don't leave it in the base form. It's a fraction. You want to reduce whenever possible. And we don't normally write it as a decimal. We usually leave it in fraction form. So this would be 1/3. So the slope or the pitch of this roof is 1/3. So that kind of gives you an idea of the slant here. Now, I'm not a roof expert, so I don't know if that's like a steep roof or, I don't, they might be like, if you convert that to decimals, 0.33 repeating. So there might be slopes that are less steep, that might be 0.25, or steeper roofs. It kind of depends on where you live. Because I know when I lived further north, you tended to have steeper roofs because you wanted the snow to kind of fall off the roof. But that's what slope is. And actually, when I lived up north, there was a colleague of mine that you asked me for help on the slope formula because they were building a house and they wanted to have a specific pitch on the roof, and so they needed to know what the dimensions they needed to have. Like if you're like, okay, I've got this far, how high do I need to make this to have the correct pitch for the snow to come off? So we were actually able to use the slope formula to help her out so they could build their roof and have the right the pitch that they wanted. So very useful concept. So next one, example here is stairs. And stairs usually have, you probably notice most stairs have the same sort of angle, there are some stairs that are steeper than others, but those have been kind of standardized on the distance you have going up versus over. They want to make sure that stairs kind of have a consistent slope. So here, our rise is 10 feet and the run is 18 feet. So our stairs are going up 10 feet and then over a distance of 18 feet. So again, the units are canceling. We're getting 10 over 18, which then you can reduce. I can divide those both by 2. I meant to do that in a different color. That's because it's 5/9. So again, there are no units on this particular measurement because the units canceled out, but that is our measure of slope. Are there any questions on these two examples? Okay. So hills, this is sort of relating to roads, or you're going up a hill, might have certain different certain angles and different steepness. So anything that you can basically form a triangle with, you can find slope, because when you're looking at the slope, you've got something that is, this hill is not perfectly straight, so it's not a perfect line, but on average, you can make it a line. So I'm gonna try to do my best to make it a straight line really badly, but it's almost a straight line, so that's good enough for considering like the slope. And you can see that you're doing how much you're going up and how much is over, so you're basically forming a triangle. So you can find the slope of anything where you can kind of just find a triangle if you do like a cross section of it. So for our hill, so it's always rise over run. So we're going up 300 feet. And we're going across by 1,000 feet. So the feet cancel. So we have 300 over 1,000. And then we can reduce. What's nice is when you have zeros, you can basically just cancel out the zeros. It's one of the wonderful things about fractions and powers of 10. And this gives us 3 over 10. So that is the slope of this hill. Now, what's really nice about slope is, like, let's say you didn't want to go all the way to the top of the hill, you could pick any point and find the slope of that smaller section, and you'll get the same slope, assuming that it is rising at about the same rate, that it is looking fairly linear. So if in blue, if instead of doing the 300 over 1,000, I found whatever that vertical height was at that blue point, and then the vertical distance that way, and found that slope, you'll get the same slope because it's got the same amount of change all the way up. So that's a really nice property of slope, is that you don't have to be at the maximum height and the maximum vertical distance as long as it's got the same steepness basically the whole way up. So same thing with storm drainage pipe here, is that if you didn't want to go the whole 80 feet, you might be looking at just a smaller section to get an idea of the slope and the steepness here. And slope is really important when you're talking about pipes, and because you want to make sure that it's not flat, it's not a slope of zero. You want to make sure that it really does drain, you know. So for drainage, you actually want to have a negative slope because you want it to be going down. So all these examples that I've done we're increasing as we're moving from left to right. So when you've got this drainage pipe here, we're actually going down because we want to decrease. We want to make sure that things are, you know, everything is draining. So when we write our equation for slope here, oops, I'm in the wrong color. So it's rise over run, but we're not rising anymore. We're not going up 5 feet. We're going down 5 feet. And so we indicate that with a negative. And so we'd put a negative 5 feet, but we're still going horizontally to the right by 80 feet. So you want to, the key thing is to remember that it's going to be a positive slope going up, but if it's going down, it's going to be a negative. And so whenever we've got distances that go down, we use a negative value for that to indicate that it's going down. So that gives us negative feet going down. So our units of feet cancel, and we have -5 over 80, which we can reduce. So I can divide those both by 5. Which gives us a -1 over, just grabbing my calculator, 16. So the slope of this drainage pipe is -1 over 16. And if you are more comfortable to think of that in terms of like decimals, you can divide that as -0.0625. So negative slopes, you want to think these are going down, positive slopes are going up. Any questions? Okay. So grade of a road. So if you were told there is a 2% grade, what does that mean? So think of 2%. Percent mean it's over 100. So you take your number, 2.5, I said 2.5%. You write it over 100. You've now turned it into the formula for slope, basically. We've got 2.5 over 100. Now, we don't like to have decimals in fractions. That's the thing that we don't want to do. So in order to get rid of 2.5, we can multiply that by 10 to get 25. But then I also have to multiply the denominator by 20, or by, I said multiply by 25. Multiply by 10 to get to 25. You also have to multiply the denominator by 10. And we're doing this so that we don't have a fraction or a decimal in our fraction, because we just don't like that. So that would be 25 over 1,000. And then you want to reduce that. So I can divide those both by 25. That gives me 1 over 40. So that is the slope. So 2.5% grade. This is a very flat grade. What does this actually mean in terms of a road? What this means is, if you think of it, we've got rise over run. It means you're rising by 1 feet or 1 foot over a distance of 40 feet. So that's a very, very flat, almost flat, road. It's got a slight incline, but not a very strong one, because out of 40 feet long, you're only going up 1 foot. So that's what grade of a road is telling us. So 2.5% grade is a very almost flat road. When you've got higher grades, that's going to be more steep. So you can always convert your grade of a road to kind of putting this in context of like how many feet are we going over a specific distance. But you would have to first convert your percent, your number, to the fraction form of the percent. Then you have to reduce that fraction, and then that kind of gives you context here that you're rising 1 foot over a distance of 40 feet. So that's grade of a road. Is what they'll normally do is they'll go the opposite direction. They'll measure the rise over the run, and then they'll put that into decimal form. So 1 divided by 40 in decimal form is 0.025, and then they'll convert that to percent by multiplying by 100. So that's what grade of a road is. So you can kind of, these are interchangeable concepts in a way, that like the percent is related to the slope when you're talking about grade of a road. And then pitch of a roof. So this is, we had another one with roof, but in this case, we've got the middle height is 7 feet, but we know the total span. So the way that roofs are designed is that, you've got 24 feet. So that's in the middle. You want the pitch, the highest point of the roof, to be in the middle. So that means our distance here is 12 feet under the part that we're looking at here for the pitch of the roof on one side, is that we're actually looking at a horizontal distance of 12 feet. So our slope in this case, it's rise over run, so 7 feet over 12 feet, which is just 7 over 12, and those don't reduce. So that is the pitch of your roof. And if you put it as a decimal, so you just divide that in your calculator, you get 0.583 repeating. And so if we compare that to our other roof here, the 1/3, which is 0.33 repeating, the 0.33 repeating is not as steep as a roof. So this roof, the 7 over 12, is steeper because 0.583 is larger than the 0.33 of the other roof we were looking at. So you can even kind of compare pitches to see which one's steeper. I usually, when I'm comparing something like that, I compare in the decimal version, because comparing 7/12 to 1/3, in order to really compare those, you'd have to get a common denominator. But it's easier to just get the decimal version, and then you can see pretty quickly which one is actually bigger by comparing them in decimals. So when I'm comparing slopes and their fractions, I will generally convert them to decimal form in order to do the comparison, because it's just a lot easier and you don't have to try to get common denominators there. Any questions? Okay, so this is my final example. And this is sort of, again, talking about slope. And now we're not looking at pictures and rise over run. We're going to talk about the meaning of slope and what that actually means. So this is sort of like a business example. This is very vague, specifically to focus on the meaning. So The slope of lines representing annual sales Y in terms of time T are given below. That sentence is saying that we've got sales of something, and the graph basically is the vertical is measuring what the actual sales are, and then the horizontal is over time. So you might have each year, and then you might have a number here. So you might be, doing it by year, by day. That's what they're describing here. Use the slopes to interpret any change in annual sales for a 1 year increase in time. So that 1 year increase of time is telling us that our horizontal distance is 1. The run is 1, so the units are years. And so then the rise is the amount of sales, which are always in dollars, unless you're told it's millions of dollars. So we're assuming that it's in dollars. So we've got units here. So our slope, which is rise over run, is our run is across 1 year, and then the rise is whatever the number is in dollars of sales across for 1 year. So this is an example of slope that has units, because we're not comparing the same units. We've got different units, but we're looking at it as something over time. So this is usually an average rate of change kind of thing, where you're looking at how does something change over time. So if the line has a slope of 135, so that is equivalent to 135 over 1. So if you've got whole number slopes, you can always convert them to a fraction by putting them over 1. And so when you look at your units, I always then put in my units there after I do that. It's going to be $135. That's our sales. And then this is over 1 year. So when we write an interpretation of slope, we're writing a sentence of what this actually means. And so if you have a line that has a slope of 135, this is a positive number, which indicates an increase. So we would say the annual sales, and it's positive, so we say increased by, and then how much it's increasing by. It's $135. And then you would give your horizontal, in 1 year. So when we're interpreting slope and you're writing a sentence of what that means, you're usually saying, okay, what am I measuring? Which is the Y. Is it increasing or decreasing? So you give like a direction. You give the amount, it's changing in Y. And then you give the amount it's changing in X. And this is the format that we do for every interpretation of slope. So for a slope of 135 in this situation, annual sales increased by $135 in 1 year. We're just assuming dollars unless they told us it was like, other units. Next one, we have a line that has a slope of 0. So 0 means that it's flat. If we were to write this as a fraction, it would be 0 over 1. So 0 means there's no change, no vertical change. So in 1 year, this is telling us there was no change in sales. So we would literally write that, in 1 year, there was no change in sales. So it doesn't mean there was no sales at all. It just means that the number last year and the number this year were the same. There was no increase or decrease. It was stable, which is not a bad thing. Then the last one here, so the line has a slope of -40. So this would be, you write that as a fraction, you got -40 over 1. So that negative means we're going down. There was a decrease in sales of $40. in 1 year. So it's kind of like you're writing your sentence the same way we did with the 135, but we're changing increase to decrease because it's negative, it went down, and then we're changing the numbers. So the annual sales decreased. And when you say decrease, you don't need to include the negative anymore because the word decreased already takes care of that negative. So we don't say it's decreased by negative 40, we say it's decreased by 40 in 1 year. I should probably spell out the word year, but it's you get the idea there. So slope is, when you've got a slope, it's a really good way to compare how things have changed from year to year to year. And that's what we mean by average rate of change, is that if you've got the amount of change over a certain years, you're dividing by the number of years you're looking at that change, and it gives you about an average how much each year that it increased, whether it's increasing or decreasing. And of course, if you're selling something, you want to have a positive increase. So if you start seeing that you've got decreases, well, that's a problem. So the concept of slope is really important in businesses to kind of look at how you're growing and how your company is doing. Are there any questions? Okay, so this was my final example on basically what slope is. So from here, you'd want to watch the video that I have on basically the slope formula, where we're using it with actual ordered pairs and graphs. So you can start getting it out, you can see what it means outside the context of real life, and you can understand the algebra portion of finding the slope.